Hello everyone, and we're going to be looking at day 8 of Lean. I guess if I end up changing this, maybe it's not day anymore, but this is going to be looking at negation. And negation is really fun because you can just prove that things are false, things like that. So a proposition being false does not mean that a false proposition is true, but that given a proposition, there can be no proof. So this is expressed by given some proof of P, a contradiction is derived to form a proof of false. And this is often like proof by contradiction. So not P, in this case, is going to be defined as P implies false. And that probably makes sense or might not make sense, but we're going to show that it does work in Lean. So we have a variable P, and that variable is a proposition. Then we can say that it's actually the same, not P is the exact same as P implies false. So we have theorem, let's just call it same, it's been really easy. And we're saying not P, and you type the not by just doing backslash in OT. And then we're gonna have the little P equals, and we're gonna do P implies false. All right, and then we gotta prove it. So colon equals, and this one, because it's the same one each side, right? We can just use RFL. And so we can tell that type checks, so we're all good. So that's something we're gonna have to keep in mind for later. Not P is the same as P implies false, right? So how do we like prove some like simple proposition, just like really simple? We're not gonna go far into it, but let's look at like theorem z ineq, so like 0 not equals 1. So 0 ineq 1. So how do we prove something like this, right? So Lean has like a really nice way of proving super simple things like this, and that is the dot notation. So you can put a little period on things if it's really simple like this. In most applications, I'm not sure if it's going to work, but if you need to use something like this, it's perfectly acceptable. And we can look at the same one as well. Well, by which I mean same up here. So we can show, let's say, theorem 0 not equals 0 is equal to 0 not equals. Yeah, that is a mess. All right, it doesn't matter what the name is, but we're gonna have 0 is not equal to 1, right? And that's going to be the same as not 0 equals 1. Oh, we have both of these. There we go. And just as before, we can pretty much just prove this with the reflexive property, right? Because we're saying that a not P is the same as like a P implies false, right? And if we want to go back up to this dot notation, it doesn't just work with natural numbers. You can also get it to work with booleans. So true does not equal false, right? Makes sense. TT not equals false, right? And we can just end that with a little dot. So this is some really simple negation stuff. So how does like Lean know that 0 does not equal 1? Well, it has to do with a disjointness of constructors. So how does Lean interpret natural numbers? So let's just go ahead and reduce nat.0. Just saying the natural number that is 0. Now this is kind of like an inductive type, but we're not going to talk about that yet. We're going to do that later because I don't think it's too important. And Lean knows that it's pretty much a 0. It's just equal to 0. Makes sense, right? So how do we get from 0 to 1, right? Well, obviously, we're just going to add 1 because these are natural numbers, so we can't have like 0.5. So what is the successor to 0? Well, the successor is going to be 1. So nat.suc is of 0, right? So what is the successor of 0? And that's going to be equal to 1. And you can actually find out if you just keep doing this. it'll actually just increase in size. So what is the successor of the successor of 0, right? So it's just 0 plus 1, which we get 2. So I hope that makes sense. I think it should be pretty self-explanatory, right? So let's go back up to this 0 does not equal 1 and think about how lean knows some of these items. So let's say we have theorem 0 is not equal to 1. I'm going to put a little single quote, just like primed, make it different, right? So that 0 equals 1 implies false. Remember, this is the same as just not 0 equals 1. And so we're going to have to prove that. But this time we're not going to use the dot notation. Let's go ahead and try the lambda notation. All right, so lambda, and let's have a hypothesis, h, that 0 equals 1. Okay? We have some hypothesis that 0 equals 1. And what we see here is that this says that given a proposition that 0 equals 1, we return false. All right? So it's actually a really good way because lean actually knows how to see that 0 isn't equal to 1. Or just like most natural numbers that aren't 0 can't be 1. So like 0 isn't equal to 2, that's gotta be wrong. And lean knows some of these things. It's not a complete idiot. So you can actually use nat dot no confusion. You probably won't use this one much as well. But lean knows that this isn't true, and it'll solve this for you. All right. So I wouldn't worry too much about nat dot no confusion. If you're taking like discrete math, like UVA's CS 2102, probably won't be too much. But this is a good thing to know. Oh, we can also like look at a begin and end. So 0 equals 1 implies false. We can just look at what it would look like in this. So in this is basically an assume. So assume, let's just call it H. Right, so we have a hypothesis 0 equals 1, and we need false. So there's a nice other little way that you can do this, and that is dec trivial. It's just decimal trivial. So a really nice way of proving this one without using nat dot no confusion is you can just assume that, let's just say have, I'm not sure if we've talked about some of these items before, but I think we have. So let's just say have, let's just say 0 equals 1. Actually, that should be a z. And we know this is pretty much false, right? So let's say 0 equals 1. Actually, this should be not equals, my bad. NEQ. Right. And then we need to prove this one because you always have to prove some of these. And we're going to use dec trivial. And so lean can just know that 0 is not equal 1. It makes sense to it. So now we have a secondary hypothesis, 0 equals 1, and 0 does not equal 1, right? So what we can do now, finally, is we can say this nice little keyword, contradiction. Contradiction basically goes into the tactics right here, and it looks for two things that are contradictory. So in this case, 0 does not equal 1 completely contradicts the proposition that 0 equals 1, right? It's impossible to have both those states existing simultaneously. And so the contradiction looks for something there and finishes that section of the proof. All right? Because we're looking for false. So if we have two things that contradict, this whole thing's gotta be false. It's gotta be false. Okay, so now that we got through that, let's look at a common assumed show from proof pattern. So if we want to edit this, because I think if you do some discrete math, I think this is probably important. So I just want to cover it really quick. So assume show from is just a common way that we can prove things. It's not necessary, but I think it might be a little bit helpful. So in this, we have to assume something. So we assume H. And actually, if you want to expand on this, and if you want to make it more readable, you can just set 0 equals 1. It's not necessary. Another way you can do this is intros. And it'll just make like A, B, C, D, etc. I'm pretty sure. But in this case, like if you want to assume things individually, you can do it this way. You can also give names with intros. So if I do HYP, it'll name the first one HYP, the second one probably A. I'm not completely sure, but that's another way you could do it. But in this case, we're going to use assume because that matches that proof pattern. So we can keep this, but we're also going to want to put a front show. So in this case, we are showing that it is false. So show false. And so this actually is almost like just a little bit of syntactic sugar at this point, because we're only trying to prove one thing. If you have multiple turnstiles, show can, I believe, can actually switch which one you're proving at that time. So that's the little item right here. And we can test that out later. I don't want to give you false information, so take that with a grain of salt for now. So let's go ahead and do this sort of thing. Actually, we can just do, let's see. I wonder if we can do this. It implies false. Yeah, we can. Yeah, so remember, this is basically the same thing. All right, and if we want to do a from is basically the same thing as exact, if you remember that. So we can do from 0 is not equal to 0 and H. So what this basically does is it has 0 is not equal to 0, and that's almost like a function. So it's inputting something that's 0 equals 1 and outputting false, if that sort of makes sense. So we have H, which is 0 equals 1. It gets put into here, and then this outputs false. It's like an argument, sort of. So when you exact false, you've proven the theorem right here, and you're done. Hopefully super simple, at least I hope. But that's how that one's done. So let's look at a proof by negation. So proof by negation may be used when you want to show that a false proposition is false. And to use it, you would take a proposition and form a contradiction. And with that contradiction, you know that it must be false. So let's say theorem proof by negation. And this is something which we'll talk about a bit more later, but it's for all. So you do that by typing \all. I think you do \for all as well. I think we can highlight it over it and it'll tell us. Yep. So it's for all P that are propositions. P implies false implies not P. Oh. Right? So P implies false implies not P. That's pretty obvious, right? They're essentially the same thing. So how are we going to prove that? Or at least for this case, so you can do lambda. So we're just saying we have some P, that's a proposition. And we have P, which is a proof that P implies false. And we're just going to basically pop out P right here. And we're pretty much done. It's actually really simple. So that's basically what we just talked through. Just really quick. Just this item right here. So how can we use this? So we're going to use it just one really quick way. I don't think knowing this probably isn't too important, but there's some concepts behind it that might have been important. Oops. So actually, let's do a lemma. Remember, lemma is like basically a theorem, just a bit lower level. I just want to show that it's another option. So let's say z is not equal to 0. I don't remember actually how many we've used of this, but I think it's probably the fourth one. Is not equal to, so not 0 equals 1. And begin. So we're going to use a begin and end. And then we're going to go ahead and apply proof by negation. So that basically takes the turnstile here, all right, and it basically kind of breaks it apart a little bit. So like unfolds what it kind of is. So in this case, we had a not 0 equals 1. And we're just saying that 0 equals 1 implies false. Remember up here, we showed that these two are pretty much the same thing, right? So there are no problems with that. So how do we just go around solving this? Well, you can just do assume or intros. It's up to you. But we can do assume H, which is our hypothesis. We can just do 0 equals 1 if we want to write things out. You can just do assume H. Lean will know. And then we're going to show false. Again, this isn't really necessary, but for the proof pattern, let's go ahead and use it. And we did a contradiction earlier. So let's go ahead and use nat no confusion this time. So we can do from nat dot no confusion and H. And we're done because this outputs false. So that means that we have solved our turnstile and we are done. All right. So let's see, that was the proof by negation, right? Proof by negation. Next thing we're going to look at is modus tollens. So that, remember, I don't know if you know this, but it basically says that not Q implies not P from P implies Q. So I don't know if we used this example earlier. So if you have P, which it's raining, and then Q is the streets are wet, you can deduce that if the streets are not wet, which is like a not Q, then it is not raining. So I'm going to go ahead and write that out just so it makes a bit more sense. P is if it's raining, Q is then the streets are wet. Actually, technically we don't have an applies, so let's just say the streets are wet. All right, so if it's raining, the streets are wet, okay? And that's generally going to be true. Let's not come up with some crazy counterexamples. It's under a bridge. Okay. In general, this is going to be true. So we can say that if the streets are not wet, okay, then it is not raining. See what I mean? So P implies Q. You can also do not Q implies not P. All right? So how are we going to write this out in lean? So we're going to do a theorem. This is modus tollens. And we're going to go ahead and do that for all again. We're going to talk about this later. P, Q. So we have two propositions. And then we have P implies Q. All right. So our if P, then Q. And that implies that not Q implies not P. All right. So that's basically what we just went over. If it's raining, then the streets are wet. Implies that if the streets are not wet, then it's not raining. All right. So how are we going to go about solving this? You could do begin and end. We're going to do lambda notation this time. Just got to keep things fresh, right? I don't know. So lambda, P, Q, and these are going to be propositions. And then let's say we have a proof of P to Q. And that's going to be basically this right here, that P implies Q. Remember that this is essentially the same thing as an assume. So if you use begin and end, you can just say assume PQ or props, assume proof that P implies Q, right? So that's basically our first set. Then we gotta break things down. So proof that, so we have from not Q. So once this goes away, we just have not Q implies not P. So that means we can assume the not Q. And I'm gonna write it out. All right. Proof of not Q. And then let's do another assumption. So at that point, we just have, I believe, not P. So we're gonna assume P. All right. And then finally, after all that hard work, we can use the proof of not Q of the proof of P to Q on the proof of P. And I'm going to walk through this really quick. Actually, why is this not type checking? Oh, whoops. I don't want that. Okay, so what have we done? So we've assumed two propositions, P and Q. All right. And then we have this proof of P to Q, which we got right here from this first section. And then we have this proof of not Q. So after this, we are only left with this in the turnstile, or this left to prove. So we're going to assume that we must have some not Q, which is what we've done right here. Then if we're solving for not P, we're going to assume that there is some proposition P or a proof of it. And then we're just basically using all of those tools, so to speak. And we're going to say proof of P to Q using that proof of P. So the proof of P to Q takes in a P, outputs a Q. So using the P, we get Q for this. And then if we have a proof not Q, we've basically turned up with false, and we've solved it that way. So let's go ahead and see what would happen if we tried to do a begin and end. And then we're going to go ahead and simplify that one, because this one's pretty long. Alright, we got to change the names. So begin, end. So remember, there are two ways we can do this. One is just intros. And you can see that basically just goes ahead and proves everything. I guess it does A1. Probably do A2 afterwards. So we have P and Q that are propositions. We have a first hypothesis that P implies Q, which we actually did right here. And then we have not Q, which is the same as this right here. So we did this all before. It's nothing new. So we can do intros with P, Q, what do we call things before? PF, P2Q, and proof of not Q, if we want to rename everything. And then we just gotta look at some of this right here. All right. So let's go ahead and assume that we have some proof of P, because what we've got right here is not P. And remember that not P is the same as P implies false. So if you have an implication, you can assume P, right? Okay. So now we're only trying to solve for false. So you can kind of like map some of these too. So P would interject here. So P to Q. So now we're at Q. Q to Q implies false. So Q to Q to false. And so once you map that through, this all turns to false, and this is solved. All right. So we can exact that proof of. So the first thing we're doing is we're taking the proof of P to Q and applying the proof of P, right? And that gets us a Q. And then using the Q, we have proof of not Q, which is, again, Q implies false. So this whole thing turns up with false. False matches the turnstile, false. Exact that, we're done. Right? So that is some more stuff in Lean. Ooh, this is a long section. Hopefully this isn't going too long. I'm sorry, guys. The next thing we have is, I think we can go over, is non-contradiction. So let's just make a comment. Non-contradiction. So a proof of any proposition Q and also its negation not Q gives rise to a contradiction, which is a proof of false, right? Therefore, this is impossible, and so for any proposition Q, it must be that not Q and not Q. Because, let's write it out real quick. Not Q and not Q, right? Because if you have an and, then if one of these is false, the whole thing is false. So assuming Q is like actually real, then Q and not Q is completely impossible. So that should always turn up with false, and the not of something false has got to be true. Super little simple thing. So let's go ahead and write this on in Lean. So no contra. So we're going to use that for all again. So for all Q that are propositions, we could name this P, but we've used Q before, so we're going to go ahead and do that. And we're gonna write that thing out we just did, Q and not Q. And how we're gonna prove this, we can go ahead and do another lambda expression. So lambda of Q, which is a proposition, and we're going to say that we have some proof that Q and not Q. So remember, this is the same as Q and not Q. This is Q and not Q implies false, right? So we can assume that. So now we get to use some of that and elim stuff that we've done before. I'm going to show you a little shortcut for that. If you do, so actually first, before we actually do the shortcut, so we have Q and not Q, and we're going to try to make a little contradiction here. So if we have and dot elim right of PF, then we can also do and dot elim left of PF. So the right side is the not Q, and the left side is Q. So if you apply Q to a Q implies false, you get false, and you're done. Because whenever you get false, then everything is solved. Unfortunately, I don't know. No, that's good. Otherwise, these would be impossible. All right. So there we go. Now a little shortcut you can do. Instead of and dot elim right, you can just do and dot right. Same thing with this. You can do and dot left. And I'm wondering if you can actually just do right. No, I don't think you can. Right? So that's a little sneaky way of making it shorter. Wonder if you can do 1 or 2. Nope. Alright. So instead of elim right, elim left, just go ahead and do right and left. I think it makes more sense too. Alright. So let's apply that just really quick. If we have some variables, these are just arbitrary variables. Let's make them nat. So you can either do nat by typing it out or \nat, up to you. And then say theorems in CAB. Doesn't really matter what you name these. But we're going to do not A equals B. And A is not, whoops, A not equals B. All right, so what are we saying? We're saying it must be the case that A equals B and A does not equal B is false, right? This is totally impossible. If you come up with some solution for this, the world is going to explode. And we're saying that this must always be false, thus this must always be true. Because we have a little not here, right? So let's go ahead and do just begin, and because we've basically done this up here with this theorem, it's basically done all the work for us. We can just do apply no contra. We can go ahead and check what no contra does. But of course you can see what it's doing right here. And there you go. For all Q is a prop, it's not Q and, well, not Q and not Q. And so this is basically identical. So pretty much knows. Yep. So it basically works backwards on this to prove it. All right. And we can go ahead and actually do the reverse. So we don't have to apply this no contra shenanigans. We can do it ourselves for really cool. Are we really cool? Oh my. Okay. So I'm gonna go copy paste this so we don't have to write it out again. And then let's see, begin, end. What do we have to prove? Just this right here. And we already have the variables because we declared them here. So no need to go ahead and assume them. So we can do begin. So let's just go ahead and assume C. C is just everything that's not part of this knot. So just this whole section right here. All right. And then let's just do have the left of this is equal to, oh, I think I remember it now. So if you do C dot 1, then you get the left side. If you do C dot 2, then you get the right side. So like this is a shortcut of this right here, which is a shortcut of ilm underscore right. So makes it less readable, but it also makes you look smarter. I don't know if it makes you look smarter. So let's say we have false. I'm just shortening for F, and that's just R and L, as we did right here. It's the same thing. And then if we look in our items, our hypotheses, we have this false right here. And we know that this false matches the turnstile false. So our clever little way of doing this is assumption. And assumption is really nice because it takes the work out of doing like exact F. But it's also very weak in that it can't do much more than just look for a hypothesis that matches the turnstile. This is all it can do. But it's nice. It's one of my favorites, actually. All right, so next we have our list to do. I've not really scripted this, but just kind of going off. Is negation elimination. Because of course, everyone wants to know what happens if you do a not. So if you have not P implies P, right? And it makes sense, right? That you'd be able to do it. But it's also not constructive if you know what constructive proving is. I don't think it's called extractive proving. But because we only have P implies false. So it's kind of weird to do it twice. It's hard to explain, but it's all about constructive logic and classical logic. Classical logic, this totally works. Constructive logic, not so much. But so we're gonna have to do the classical excluded middle to solve this properly. So let's make a new little thing for it. Classical excluded middle. I'm sorry that this is a little bit hard for me to explain. I'm not a teacher in this. But so in constructive logic, a proof of not P is a proof of P implies false, which we've already shown this works completely fine. We've used it tons of times. And we interpret that as a proof that there can be no proof of P, right? So a proof of not P is therefore a proof that there is no proof of not P. And in constructive logic, however, knowing that there is no proof of not P is not the same as having a proof of P. So like in symbolic terms, like from the assumption that P implies false, you can't derive a proof of P. So that means we actually have to have this idea of the excluded middle, that for any proposition P, it's either that P is true or not P is true. And this seems really strange, but it's how it works. So let's make a new axiom. Or like axioms are like kind of dangerous because you can start doing crazy things, but this is fine. It's fine. So for all P, it's either going to be P or not P. The other way we can do this is excluded middle, and that we have some proposition P, then oops, P or oh my, or there we go. And so, oh, forgot to change the name on that. I was like, why is this yelling at me? So that's a perfectly good way to do that. Sorry, I was checking something. Okay. So now that we have that settled, how are we going to go ahead and use it? So Lean actually has their own excluded middle. It's called M. You know, EM for excluded middle. I think it's pretty self-explanatory. And the way you get access to it is you open classical. And this basically opens the namespace classical. If you don't know what a namespace is, you can look it up. But it's basically just a collection of tools that you can use. We'll do more open stuff later on, especially when we actually work with inductive types. So if we don't want to name this theorem, we can use example. And our example is that for all P, actually all propositions that are P and R, then P implies R implies, this is what we're going to be proving, implies not P implies R implies R. Ooh. Didn't quite get to the end. That's close. I think in previous ones I was trying to, I thought the font was a bit small, so I've upped it this time. Hopefully it'll help. So let's look at what our tactic state is. So for all P and R, which are propositions, P implies R implies that not P implies R implies R. So this might look hard, easy, I don't know. So we're going to go ahead and, so we've already done the beginning and end, so we're going to assume, of course you can do intros. I'm going to do just assumes. I like assume more. So assume that P and R are propositions. And then I'm going to assume PR and NPR. So what this does is it just looks at, oh, here's PR. And then once this goes away, it's like, oh, this is what we're left with. So we're going to go in and assume this next section. And then we're left with only R. And now we're left with only R. So how can we keep going, right? So we've decided that we can only have one version of P, right? It's either, if you have a proof of P, it's either P or not P. No other options. Can't be like some weird in between. I don't even know. But constructive classical logic. Yay. Okay. So we're going to go ahead and use that. So cases on EMP. And we're going to go ahead and name it. So I'm going to name one P and one not P. It'll make sense, right? Because we have the excluded middle here. So a cases just breaks this up. So it's either this side is true or this side is true. And we're just going to, when it outputs it, there will be two things to prove. And we're just naming each one that we broke up. So in this case, we named this one P, and we named this one not P. You can name this whatever you want. Try to name it something that makes sense to you. And so now it should be pretty obvious how this is going to work. So we have P, which we can apply into PR. So P goes to P, which goes to R, and we can exact out the R that results from it. Same thing here. We have this not P, all right? That we can use as an argument here, which will output R, giving us R. So let's go ahead and write that out. Can exact PR and P. All right, and that solves the first one. And then we do the exact same thing with exact. Just this time we're using NPR and not P. Woo, we're done. See, that's not too bad, right? That's all it is. So just know that classical exists. I don't think you're going to use much more than the excluded middle, but especially if you're just taking a simple discrete math class. That's probably the most you're going to do. All right. So earlier we talked about that double negation elimination. So how can we use the excluded middle to do that, right? So let's make it. So we have the theorem double negation elimination. So for all P, right, it's either not P implies P. All right. Let's do a begin and end. Sometimes you can still do lambda expressions with this. I just think it starts to get a bit complicated. And this is much easier to think through. So let's go ahead and assume that P is a proposition. Because whenever you have a for all in this, you can always assume that. Because it should work for any proposition. Next, we have this implication, so not P. So we're going to assume proof of, I'm going to just write it out. Otherwise, you end up with a lot of ends. So not P is not P. Of course, it wasn't necessary to do this. I just think it's more readable this way. And if we want to go ahead and be fancy and do that, assume show from, we can do show P from H. Actually, we don't have H. Actually, wait, whoops, I missed something. Oh no, I'm getting way ahead of myself. So we need to do the excluded middle on P. So we have a not P and a P, right? So we can do our own this time. I like that better. So cases excluded middle. Just prove that ours works. I'm not just pulling this out of nowhere. Okay, let's get rid of that. And so that we have P as a hypothesis here. So from H. right? So this left us with two propositions. In one case, P was true. The other case, P was implied false. Of course, remember, we can name these if we wanted to. I'm just going to keep it as H this time. And then we can do the exact same thing. This time, let's do a false limb. So you can do have F is false. So how do we prove false? Well, we got to use something that we already had. I'm just going to put some random variable so we can look at what our things were. So we have not P and not P. And remember that not P and not P, it's just one not off from each other. Right? So therefore, it's basically a contradiction. So we can do proof of not P and our H, and suddenly we have a false, right? So we can now do an exact false lim F. That's one thing we could do. The other thing we could do is, since this is basically a complete contradiction right there, if we go ahead and comment this out, we can just type contradiction. And we're done. It's like, oh, it's so crazy. It's lean. But that's how you can solve some simple excluded mode things, especially that double negation elimination. That caused a little bit of trouble, but it's not too bad, right? Yep. What if we wanted to go the other way around? So P implies not P. Well, you could use, I think, classical reasoning, but it should work without it. So let's have let's make a little definition, or you can theorem or lemma. It depends on the use case. And we'll do something. I don't even know what I would call it. Let's just call it double neg. I'm out of ideas. So let's say we have P implies not P. Because I think we already have P as a variable somewhere, probably. Alright. So P is a proposition, right? And so we're going to go ahead and assume the first P. Assume that P is a proposition. Oh, whoops. Actually, we already have it, don't we? Oh yeah, we already have this. Forgot variable. So we're going to assume that there's some proof of P. And then we're going to just say, assume that, can't write assume. I'm going to call it NP for not P. That P implies false. Where am I getting this from? I'm just getting it from here. That's all it is. If you're doing this yourself and like UVA's scream out, my word of advice, just assume things till you can't assume anymore. Terrible way of doing it, but it works. And then we can do two things. We can do exact in P and P, which works the same way as above, or we can do the same thing as above at the end, which is just contradiction. And voila! Magic. Not really magic. What if we want to do this with lambda expressions? If you're in love with those, let's change the name. If you really want to do a lambda expression, you could say that you have some proof of P. Whoops. And from that, you assume that not P is a proof of P implies false. We're just going to assume that, you know. And then you can do the same thing as before, where you apply not P to P. And you're done. Woo! This is long. I forgot how much stuff is in negation. But we're almost done. We've also almost reaching the 1 hour mark. So that's kind of scary. So proof by contradiction. I think this will... Oh, well, I think that we still need to go through the proof by contrapositive. So let's power through. I hope this is making sense. I'm sorry if it's not. Ask your consult Lean's handbook, or if you have a professor, consult them too. So, a proof of contradiction, unlike a proof negation, works by assuming not P. If this leads to a contradiction, then not P must have been false, and P is true. So this uses double negation elimination, as not P implies false is the same as not P, right? So a proof by contradiction aims to prove P. I think there are some really nice proofs online. I think there's one that involves square roots and squares. I'm not sure what it is, but I actually like that one a lot. So in other words, proof by contradiction is used when you want to prove P. So you can show that a proof of not P is untrue leads to a contradiction. So a proof of contradiction relies on the law of excluded middle, because not P is interpreted to mean that we can prove that there does not exist a proof of P. If that maybe makes sense. Hopefully it does. However, unless we assume that P has to be either true or false, we do not know that proving there is no proof of not P implies that P must be true. That was definitely a bit. I'll say it one more time. So, a proof by contradiction relies on the law of excluded middle, because not P is interpreted to mean that we can prove that there does not exist a proof of P. Okay? However, unless we assume that P has to be either true or false, because remember that's what the excluded middle does, we do not know that proving there is no proof of not P implies that P must be true. Whew. All right. So let's go back to the bottom. So let's say we have the theorem, that is the proof by contradiction. So for all P that are propositions, I'm definitely going to talk about for all next. I think it's really important. I mean next day. I don't know why I call them days. So applies P. And how we're going to do this? So remember, you just mentioned that it's basically, this is just double negation elimination, right? Not P is the same as not P implies false. So that's this right here. So we can do double negation elimination. All right. Using previous items to prove future ones. That's just how it is. And there we go. I believe you can also, I think you can add an @ symbol, And that would turn off type inferencing, but in this case, we don't really need it. All right. So let's prove something super simple. Theorem 0 equals 0. The easiest things to prove, because you could just do RFL. But no, we're going to do a proof by contradiction. So how do we do that? Let's do add a begin and end. And then we're going to go ahead and apply our proof by contradiction. All right, and remember that this basically works on that turnstile. So we're going to say that not this proposition implies false, right? So that's what we have here, I believe. Okie doke. So now we're going to assume proof. Yeah, I can't really think of a better name. So that's 0 equals 0 implies false. All right. And now we have this not 0 equals 0 and false. Okay. And if we want to do that assume show from, we can do show false from, remember that's same as exact. I think it actually tells you that too. A synonym for exact that allows the writing of the have suffices show. Close enough. All right, from proof, and then we're gonna do eq.refl of 0, because remember that just gives you 0 equals 0. So if you have 0 equals 0 implies false, and you give it that argument, you're getting false. And then you're exacting false. So you're done. Woo! Okay. This is a lot. This is quite a bit. So what else could we do? I think that's the only really important ones I can think of for proof by contradiction. But that's the basic idea, is that you assume that your item is wrong, and then you show that that assumption was incorrect. And that's what proof by contradiction does. So, I think there's some really nice math proofs online. Go look for one. You might like it. I don't know. All right. So next thing on the bucket list. Yeah, okay. So we had, what did I say? Proof by contrapositive. So, man, my voice is about to die out. Okay, the aim in a proof by contrapositive, okay, is to show that P, so like two propositions, P and Q, from an assumption of not P and not Q. In other words, not Q implies not P, implies P implies Q. I can write that out real quick. So, not P and not Q, or not Q implies not P implies P implies Q. Another way to view this rule is that it aims to show Q from first, a proof of not Q implies not P, and second, a proof of P. The way to think about this latter view is that it says if Q being false implies that P is false, and if we know that P is true, then Q must not be false. And so, like by the axiom of the excluded middle, Q has got to be true. All right. It's a lot. So let's just go ahead and show what it looks like. Okay. We gotta break this down, right? So let's say we have the theorem, proof by contrapositive. Hopefully I wrote that right. And so for all propositions P and Q, I'm gonna steal this. All right. So we have our not Q implies not P implies P implies Q. I'm not great at the proof by contrapositive. It doesn't really make quite as much sense to me, but I think it's important to include in this just in case you need to use it somewhere. So how are we going to do this? Yeah, I just saw this Steam update. Okay, so what do we have? So we have for all P, Q, which are propositions. So the first thing we know we can do is we can just go ahead and assume Q and Q. They're propositions, right? First step out of the way. All right. Next, we can go ahead and assume that there's probably a not Q implies not P. In Q imp in P. All right, and now we can just go ahead and assume there's a proof P. All right, and now we've broken up so much that there's no way we can break it up anymore. We can't assume anything else. All right. So let's look at what we have here. We can't really use this. And we can't put it anywhere. So it feels like we're stuck. Right? Feels like we can't get anywhere. What we need is we just need some sort of not Q. So how are we going to get that? Well, let's look at some of the other items we did before. Right? So how could we maybe prove this? Can we use proof by contradiction? Not really. We don't have anything like this. Double negation, elimination, nope. We don't have anything like that. Excluded middle. That could be more helpful. And then we have no contra. No contra looks good. Because it's not one or the other. So let's see what we could try to look at. And maybe like things will like clear up a bit more. So I'm going to say not Q imp false. So not Q implies false. I'm sorry that this one's probably doesn't make any sense at all. It's honestly extremely hard for me to explain this one. But we're going to try to prove that not Q implies false. So it's not the case that Q is true. Wait, not the case that true is that Q is not true. Oh, yikes. Okay. So we can actually like do a begin and end in here. You could do a lambda expression, but begin and end, you know? So we're just gonna assume not Q. And then how are we going to do this next? So we have to show that this all is false using these items, right? Right? So let's make something new, all right? We have a P and we have a not Q, okay? And we can look at this not Q and we notice that we have this in Q implies in P. So not Q implies not P. So suddenly we can get this item that has P and not P, given that these two are true, right? So how are we gonna do this? We can do this in less steps, but I think it's gonna be helpful to show it out. So have in P is, what was that item? I think it was in Q imp in P, and we have to give it the argument which is in Q. Did I mess that up? Yeah, I messed that up. There we go. This binds it directly, so if you don't want to actually write out in P, not P, you can bind it directly. It's up to you, but this is another way you can do it. So what we've done here is we have P, a proof of P, and a proof of not P. Okay? And what we can do here is you could do contradiction, but then you're not really getting anywhere with it. So what we're going to try to do is we're going to go up to this no contra and have some fun with that. Because for no contra, we just need a proof. And this is and dot right and dot left. So it breaks it up. So what we're going to try to do is have P and NP is and dot intro P and what is it, NP? All right, look at all these things we're doing. So now we have proposition and not the proposition. And this is starting to get really close to the excluded middle, which we talked about earlier. So we can go ahead and exact no contra. Actually, it tells you what it is right here. So we need to give it a proposition. We're going to go ahead and give it P, and then that P and not P. Right? And so that's going to go ahead and prove that false for us, because that's essentially what it does right here. If you remember that P and then not of this. So we gave it the affirmative, it can change to the negative, give it a false. Okay. So what did this do? Honestly, not much. I just thought it was fun. But we're going to go and head into have Q not not Q equals NQF. Oh, it does not like me. There we go. Oh, did I mess this up? Oh, whoops. Right, nq imp f. I forgot that I changed the variable name. Okay. Alright, so we have this, right? And then when we end it here, we add on to our set this new one right here. That was the whole point of it. Okay? So now we can use this and we can show that we have this not queue. And then we want to show that there's a queue. Again, that doesn't change the proof at all. It's just a nice little item there. And then how are we going to get not queue to queue? Well, fortunately, we've done that before as well, right? Literally just did it too. Where is it? Double negation elimination. So for all propositions, we should be able to get from not P to P. All right. So we can do from, which is the same thing as exact, double negation elimination. And we're going to give it in Q. Oh, did I mess that up? There we go. Forgot the Q. And there we go. We are done. That is the proof by contrapositive. I'm not an expert in that one, but we can do a little example with it. So if you have, let's say, oh, we've been doing 0 equals 0 a lot. Let's just keep doing that. 0 equals 0 implies true. Remember the previous time we were just like, is it gonna be false? That's not the case this time. So in this case, we're gonna begin by applying that proof by contrapositive that we just did. Did I mess that up? Oh, I forgot the. Let's get an end statement. I was wondering why that was shifted. Okay. So, what do we have here? Not true implies not 0 equals 0. So that still makes sense, right? So we're going to assume that not true is the not of true. And we're going to assume that proof of false is not true, because remember this is just true implies false, and use true.intro. And if you don't remember true.intro from before, that's okay, because all it really does is evaluate to true. It actually says right here. So true.intro is true. It's just I think an inductive type. So if you give not true an argument of true, what does that give you? False, right? And you can see that up here as a hypothesis. So we're going to go ahead and show that not 0 equals 0. And, oh, what do we want to do this time? Oh, we can do a false alum. Probably good. So we can exact, because we have a proof of false right here. So if you ever have a proof of false, you can just go ahead and use false alum. Because we can go ahead and exact false alum proof of false. All right. So once again, the difference between a proof of contrapositive and a proof of contradiction. The method of contradiction is where you assume P and not Q, and you prove some sort of contradiction. And the method of contrapositive is where you assume not Q and you prove not P. So that's how that one's going to work. I hope this helped in some way. I'm not great at the negation items, especially these really long ones. So I highly apologize if some of these didn't really make sense. But I hope it worked out for you guys. If you're taking, CS 2102 and UVA, then I definitely hope this helped out. So thank you for watching. Take care. It's almost Christmas, so woo! Right. Bye-bye.